Fluids in motion. You know what a fluid is, right?
Yep.
Anything that flows, like air, liquids, they're all fluids. And when fluids flow, there is something that we're going to go over which is called equation of continuity. What is this equation of continuity? Because a fluid normally flows in a continuous fashion, right? So if I have a river that goes like wide, and then it narrows down like this, and again spreads out. Think of a river like this. It's wide, becomes narrow, and again becomes wide. Just out of your logic. Imagination, just tell me, like, where is the fluid going to go fast? Yeah.
Through the narrow part.
Through the narrow part. See, we know this already, but now it is put into a concrete form, that's it. So definitely there is more liquid now the same quantity of liquid is flowing through. So if 1,000 gallons are going here per second, the same 1,000 gallons will have to go here per second because it can't stay anywhere else. It's like traffic flow. Okay? So if 1,000 gallons are flowing here per second, the same 1,000 gallons will have to flow here per second, which means if 1,000 gallons are flowing here per second, if this much of fluid is going per second, that same amount of fluid must go here per second. And as you can see clearly, the speed here is V1, and the speed here is definitely different. But the area is bigger, A1 is bigger, and A2 is smaller. You know the product of A1 and V1 is what? What is area times distance? What is that supposed to be? Area times this distance. It's supposed to be volume. Area times height. What is it? Volume, right?
Yeah.
Area of the base times the height is the volume. So definitely this is the volume, and this is meters per second, which means this is the volume per second. Volume per second is equal to A1V1, and that's equal to A2V2. So wherever the fluid is going, wherever the area is narrow, the speed has to be greater. You get it? If the area becomes small, the speed has to be more. This is called the equation of continuity. Through a smaller area, the speed is definitely higher. Through a larger area, the same amount of fluid will go slower. That's why I gave the example of the river. Can be anywhere. Think of a garden hose. Okay? If you just open the tap and the garden hose is not connected to anything, just the hose, so water will just jump out like that, right? Now put your thumb or something right there and narrow the area.
It goes faster.
Goes faster. Right? That's the same concept. Or like this. If I take one full lung capacity of air and blow it out, like that. See how fast the air is flowing? Little. But do like this, you can make it go like a jet. Right? It's the same air. The quantity of air is exactly the same, but the area is reduced, and so speed is higher. So area and speed inversely proportional. If the area is big, the speed is low. If the area is small, the speed is higher. That's called equation of continuity. All right? The next one is Bernoulli's principle. You did Pascal's principle earlier, right? What's Pascal's principle? What's Pascal's principle that you did earlier? Yeah.
Forces can be transmitted by solids, but fluid transmits pressure.
Fluids transmit pressure. That's basically so pressure can be transmitted to every nook and corner of a fluid. And we went through all those things. Now this is Bernoulli's principle. It's a different principle. Now what is Bernoulli's principle actually talking about? Wherever, let me write it down. Wherever fluid goes fast, yeah.
How do you spell that?
Bernoullis.
Thank you.
Bernoulli's principle. Wherever a fluid moves fast, the pressure is lower. Wherever a fluid moves fast, the pressure is lower. Wherever a fluid moves faster, the pressure is lower. Whatever. Now, what exactly is the concept behind it? The concept behind it is this. Right now, is this air moving?
Yeah.
Here?
It's hitting it.
It's hitting it. Atoms are hitting this. Atoms are hitting here, atoms are hitting here. But there's no draft of wind, right?
Mm-hmm.
No. So it is just still air. And how much is the force acting on this side? We did calculate something.
6,000 something.
It's like 1,290 something pound force. But the same pound force is acting on this side too, right?
Yeah.
Now that's because atoms are hitting this continuously. What if I just move my hand so quickly here so that the atoms won't hit as fast on this side compared to the other side? The pressure here will drop. In other words, wherever the fluid moves fast like this, see, when I moved my hand, the paper was like moving to this side. So wherever the fluid moves fast, the pressure is lower. And that's a concept here. Look at this again. If I keep the paper like this, right now the top of the paper and the bottom of the paper absolutely not moving, right? I mean, the pressure is the same. The air is the same here and here. So the pressure is the same here and here. What if I blow on the top here? If I blow on the top, I'm going to increase the speed of the fluid. So what will happen to the pressure here?
Less pressure.
Less pressure, and the pressure underneath is still more. So what should happen to the paper?
Blow up.
Yeah. So you see how the paper is rising up. It's not magic, it's just physics. There's a lift coming up, right? And the lift is mainly because of this principle, which is Bernoulli's principle. Wherever the fluid is faster. Now, the principle actually is a more complicated one mathematically, but I'm just telling you the basic idea of Bernoulli's principle. Make sense? And Bernoulli's principle is very, very important. It's applied so many places. It is applied in so many places. What is this?
Paper.
Huh?
Gold. Airplane wing.
Airplane wing. Good. Good observation. Look at that. That's an airplane wing. Look at the wing of the plane. It's flat at the bottom. And the top is like this. Right? So when air comes in, when the plane goes forward, there are layers of air. There are layers of air. The bottom layers just keep going. But look at the top layer. What's happening on the top?
Curves out.
It curves up. That means what? There is a constriction there.
Pressure.
There's a constriction here. By equation of continuity, there is less room here. So what will happen to the speed? Speed of the air will increase because there is a restriction. So because it is squeezing itself to the top, the speed is higher. And wherever the speed is higher, the pressure is lowered. So the pressure on the top of the wing is lower than the pressure from below.
Is that why it's able to take off?
That is why the whole plane is in the air. How is the whole plane in the air? Is just by extra pressure here, less pressure here. That means more force here, less force here. That's it. The lift that the plane gets is purely by Bernoulli's principle. Why the wing is shaped like this, how the bird's wing is shaped is exactly like this also. The bird's wing is shaped in the same manner. That's why they're able to get that lift. You get it? The plane's wings, observe that, you'll see it. The shape of the wing is like that. And that is what helps it to take off and stay at the height. But it has to maintain that speed. If it drops in speed, it will start sinking. So before landing, they have to slow down, right? Before landing, they have to slow down. But when they slow down, or when they're trying to fly at a lower altitude, they have to be slower because there's more air. And the other thing is, before landing, the speed is really low, but you can't just let it go down and fall. And so the flaps and all that opens out to increase the area so that it will get supported by even at low speeds. So the area of the wing is very, very important. For planes that are flying really fast, then the area is not too important. Like the wings are pretty small, right? But for planes that are actually like heavy, like passenger planes, you need wings to be really big. The wings are really, really big. It appears to be a small wing from here when it's flying. But if you look at the actual wing, it's as wide as this. The wing is actually as wide as this room. Pretty big. I'm talking about the big planes. And it's long. So the whole area is tremendously large. So even slight differences in pressure is enough to hold the entire tons of weight up there. So every time the plane takes off and I'm just looking outside the window and trying to look at the wings, and this is the thing that comes to my mind, like pressure difference and the lift. Sometimes you think that all this weight, is it going to lift it up? Air definitely applies a lot of force. That's why it's called air force. Air force.
So when you blow on the paper, it got rid of the pressure from the air on the top. So
No, I didn't get rid of it. All that I did was, when I blew on the top, the atoms were before I blew, the atoms were coming and hitting like this. I made them kind of go that way.
So that lessens the pressure, and that makes the pressure that's on the bottom have a greater force and push it up. Okay.
Mm-hmm. That's exactly the idea behind lots of things. Lots and lots of things. Plane is one example. What about during heavy winds? How is the roof getting taken off? The roof is completely peeled off. How is it happening? Look at that. The wind is coming and blowing over your roof like this. Isn't there a constriction here? So because there's a lot of constriction, the speed of the wind above your roof is really high. The speed is high. That means what? Pressure is?
0.
Low. What about inside your room?
Higher pressure.
Because it's not moving. Inside your room, it is not moving. But outside your roof, it is moving tremendously fast. And so definitely there's a huge pressure difference. That means the force from here is tremendously big compared to the force from above. And so this force is enough to take the entire roof off.
The pressure inside is enough to take that off?
The pressure inside is big, and therefore the force is big compared to the force from above. Do you understand this?
Yeah, I understand.
Yeah. So it's the pressure difference which causes the force difference, and that's what takes the entire roof off. So why the roof is kind of peeling out is because of this. Now how can you try to minimize this effect? If there's a high wind and you don't want your roof to go off, what's something that we can do?
Lower the pressure in the room.
How?
I don't know.
How can you do that? Well, it will be nice to evacuate the room completely. If you evacuate the room, there's good. Huh? Open the windows. If you open the windows and all openings in the house, what will happen is the same wind is going to flow inside as well. Right?
The inside, but it won't take off your roof.
Yeah, that's true. You'll get a lot of garbage inside the house. Water and leaves and stuff, but your roof will still be intact. Okay? To a good extent again. Now, if the wind is really, really big, like a tornado or something, and you're caught right there, no matter opening the windows or closing the windows doesn't make any difference. The whole house is going to go. So,
Is that why they tell you to go to the basement? Because
yeah. The basement will be a safer place because what can come off is the top part of it. And so there is still some chance of holding on to the bottom. Yeah. Because concrete is not going to be pulled out, right? The concrete part of it will be still there. But yeah.
Why do some houses have those curved shingles instead of the flat ones? Because it's supposedly
curved shingles.
Yeah. Have you seen those?
Is it?
Yeah, like on the west coast, because it's supposedly more storm friendly or something. I don't
Curved shingles.
Yeah,
I've not seen those kind of shingles.
Ceramic.
Oh, they're heavier. Oh, the heavier stuff. Oh, they're heavier compared to these shingles. These shingles kind of easily come off with the high winds, very easily. High winds will take this off because it's just so flexible. The other ones are heavy. It's like stone, ceramics. So they are actually sitting there with their own weight, and so it can withstand a lot of. And there, there are holes. There are holes between the tiles. The tiles are like this. There is a gap here. So because of the gap, as soon as the pressure outside is lowered, the air will start seeping out from inside. So it is not locking the air inside. Our shingles lock the air inside, completely seal it. Completely seal it. And there they won't seal it. It is just more. Since the tiles are sitting one over the other like that, but there is a physical gap. And the gap is okay there because they're not worried about the temperature fluctuation. We don't get real winter, right? Do they get real winter? No. So yeah, there are temperature fluctuations, but not as much as here. So close to the sea, your changes of temperatures are not too much, and therefore tiles with holes and all that is fine. Yeah.
What are shingles made out of here?
Good question.
Shingle tree.
Shingles are made out of. I think it's something to do with the tar. What do you call this? Asphalt. It's a mix of asphalt with something else. And I always wondered why can't you just use metal sheets and all that stuff instead of the shingle keeps coming out all the time. Yeah, there are multiple factors: temperatures, controlling the temperature, and when sunlight hits a metal roof, it actually can heat up the entire thing so quickly. But shingles can avoid that. Shingles can protect the heat flow from outside inside, or inside to outside. It kind of controls it, not like metal. Metal has less control. But you can actually have a shingle type of material, and then over that have a metal ceiling. That'll be fixed permanently. That means you don't have to worry about replacing shingles at all. Anyway, so why the roof is peeled off again is because of Bernoulli's principle. You can see Bernoulli's principle in action in so many places. In all sports, you have Bernoulli's principle coming in. Put that away. In all sports, keep it in your pocket. Keep that in your pocket. Now keep that in your pocket. Okay. Sports. Have you heard about bend it like Beckham?
Yup.
Kick. You play soccer? No one plays soccer?
I do.
You do. Okay. So, how's that kick? That kick is a special kick because the ball is kicked like that way. So the ball is made to spin like this. The ball is made to spin like this as the ball goes forward. As the ball goes forward, the ball is spinning this way. And guess why they have seams on the ball? You have seen the seams? What's the seam for? To lock the air. So when the ball spins like this, there is a layer of air spinning with the ball. There's a layer of air spinning with the ball. So as the ball goes forward, there's a layer of air spinning that way. So look at the air coming from there now. Let's look what happens to the air coming from here. So that's the air coming from here. So what happens to this air? Look, this air will be drifted that way. Because since the ball is spinning, it collects the air and sends it one way. So where is the air moving faster now? Which part of the ball air is moving faster?
Left side.
Left side is moving faster. So the pressure is?
Lower.
Lower pressure. And here?
It's high pressure.
So what happens to the ball? It gets a push from this side more than this side. So as the ball is made to go forward, the ball is also experiencing sideways push, and so the ball kind of curves. So why is the ball curving that way? It's because of Bernoulli's principle. Okay? You can see that in action. Or I can show you this ping pong ball also. If you apply a little curve to the ball, you can see how it swings in the air. I'm going to throw it at somebody who wants it. Can you catch it?
Here's your
I
help.
can catch it. Catch it.
He's going to catch it.
No, he's not.
Don't choke.
Yeah,
Don't choke, Kate.
I'm going to swing it as well.
I feel like it's not gonna get to.
Okay, so did you see the swing?
Yeah.
Good catch. Yeah.
Why'd you drop?
Did you see the swing? Did you see how it was going?
Yeah.
Because I was spinning it that way, that's right. Okay, so I was spinning it that way. That's why the ball is curving, so you can see, like, oh, I was spinning this way, yeah. So the ball was going forward at the same time, because it's spinning this way, the pressure was lower on this side, the pressure is higher on this side, and the ball is curving, right? That's called curve ball. In baseball, it's called curve ball. That's all Bernoulli's principle. Now, again, in ping pong, in tennis, when you return the ball, you don't like slap the ball like that. How do you return the ball?
Tilt it.
A topspin, right? You create a topspin this way. The racket comes like this and tips it this way. So the ball is going to spin that way. So the ball is going to spin that way, and the air is coming from there. So it's actually not the air coming from there, but the ball is going forward. So it's like a wind hitting the air, hitting the ball, right? So what happens to the air layers? You see what's happening? So where's the pressure higher? Bottom is? So the ball will dip down. So that's why you can hit it really hard. And because you're hitting it really hard, it crosses the net and dips quickly down. And you'll be making it land inside. So you need to create a topspin. So while serving, same thing, topspin. When you serve the ball, you don't like hit the ball like that. If you hit the ball, it just coasts and goes on. It'll land outside. If you want it to actually land inside, you need to like serve it and create that topspin on the ball. And once you create the topspin, it crosses the net and dips into the box. Otherwise, it'll be fault. Same with ping pong. That way. Slicing it like that is what is needed in ping pong.
How would it work if you're like throwing a card?
Throwing it?
Like a playing card, if you throw a card.
Oh, it can be multiple directions. Like, because when you're throwing the card, depending on the tilt of the card, you can have differences in pressure. So it can actually cause, that's why it is not predictable. It flips around. Why does a flag flutter? It's also Bernoulli's principle. When the flag flutters like that, why is it taking that kind of a dancing pattern? It's because of Bernoulli's principle. You can see in all sorts of sports, Bernoulli's principle comes in. Plenty of sports. And also in boomerang, and all those things, Bernoulli's principle is doing factor. It's pretty dangerous too. Ships have collided in the past because of Bernoulli's principle. Like if two ships are getting too dangerously close, if two ships come dangerously close on water. Now this time we're not talking about air, water. Look at the water that's here. And look what happens to the water in the middle. Between the ships, is the water going fast? So what will happen to the pressure here? Decreased. And here? Higher. So there'll be an extra push from both sides and the ship cannot control itself and they'll come. So the ship can actually clash with each other.
The same thing with planes.
Same thing in?
Is that the same thing with planes?
No, in planes, of course, it's just like one wing and you're talking about the difference. Yes, same thing. See, look at the pressure is low, pressure is high, so the push. In the plane, it's different. Oh, you mean getting close?
Yeah.
Oh, yeah. When anything gets close, as you're going, even your cars or trucks, if you're pretty close, driving pretty close, very dangerous. Very dangerous, because when you drive close, the air kind of squeezes itself in the middle, and that's enough to make it go in. So it's dangerous to get closer than a certain distance. Wind can actually cause a lot of these damages. And yeah, some other stuff that I can show you. Magic. See, the ping pong ball is inside here, the cup. And I'm keeping the cup in the same way, and see how I'm taking the ball out. I'm going to take the ball out without touching the ball, without tilting the cup. I'm not going to tilt the cup also. How did the ball come out? When I blew on the top, I just decreased the pressure right here. And the pressure from under the ball was big enough to push it out. Make sense? Simple. Something that you can also do. Easy. Yeah.
You ever tried putting an egg in a ball just by using matches?
But you need to put it into something, right? Some liquid.
Like a, no, you can just put a match, like a, or spark a match, and then put it out, put it in a bottle, and place an egg on top. And the pressure on the outside will be greater than the inside, and it'll push the egg.
But what about the shell?
It's a hard-boiled egg.
Hard-boiled egg.
Yeah.
Shelled out. Shell is out.
Yeah.
Oh, okay.
Yeah.
Yeah, that understandable, yeah. That's what they do to create, take the yolk out from the thing. You take a bottle and then just keep it on top of the yolk and just leave it, and the yolk comes into the bottle, and the rest of the white is still there. That's a technique they use sometimes. If you cut open the egg, and the egg comes down, but you need only the white, not the yolk, so just use a water bottle, take the cap off, squeeze it, and then keep it on the yolk and release it. And the yolk jumps into the bottle and out. Yeah, pressure differences can cause all that stuff. Yeah, I was thinking about the shell, because I've seen another place where they put it into vinegar or something like that, and then make the shell kind of soft, and then it goes into the bottle, and after that they put some other liquid inside to make the shell hard again, so it'll be a hard raw egg in the bottle. That's something that I've seen. We look it up and see if we can do that. I mean, the other one, yeah.
Can we look it up?
Hmm?
Can we look it
Not now. We have plenty of things to do. All right, did you get the Bernoulli's principle concept here?
So you blow the air,
I blow the air on the top.
and that causes less pressure on the top, but that increases the pressure inside.
Pressure at the bottom is still locked up air, right?
Okay.
It's a locked up air, so it has to come out.
So when the pressure is lower, that means more air can come out where the pressure is into an area where there's less pressure.
Yeah.
And that's what causes it.
Exactly. In fact, all the climatic conditions, the wind and all the changes, the wind itself is because of pressure differences. The wind itself is because of pressure differences. So the weather people know exactly, like, okay, so there's high pressure here. Have you seen a weather map says H and L, high pressure, low pressure? So if there's a high pressure somewhere and low pressure somewhere, you can expect there is air going to come from the high pressure to the low pressure. And that is how they can predict which way the wind is going to blow, even days in advance, right? So there's a lot of things like this to do with Bernoulli's principle also in reality. You can also look at this. These are two cups. And the same way, take this cup off without touching anything else, like this. Blow it again. So instead of the ball, it is now the cup itself coming off. So the cup jumps out because of the lack of pressure. There's something that you can try, or you can just keep this on the table like this and tell someone, look how I'm going to separate the cups, and just blow over it. If you blow over it, the cups will separate. Okay?
Can you show us it real quick?
This one?
Yeah.
Yeah, sure.
Party trick.
Yeah, this is something that, here. it works much better with the glass cups. You know glass?
Ah, yeah.
Real glass compared to this. This is so light. It's moving. All right. There. It's out. All right. So to separate the cups, you can do that. So many things. Can you explain how this is happening? I'll show you something and explain why it is happening. That's also Bernoulli's principle. Just explain. Oops. I'm sick. My breath is not enough. Okay.
Ben can do it.
Yeah. How did that happen?
So the pressure from the side was greater, and so it was pushing it back toward you.
When I was blowing like this, why is it not falling over? Why is
Lower
it
pressure from the bottom, higher pressure from the side, and that keeps it.
low pressure from the bottom and higher pressure from that side?
Yeah,
Keeps it tucked in, yes, but why can't it just fall off sideways? Why does it have to stay in place?
All around.
Yeah.
Oh yeah, there's more pressure in other direction.
It's kind of close. The same reason as to why the flags flutter. Andrew. So same thing again. So look at the ball. When you blow air from here, the air is kind of going around, right? Suppose the ball tries to escape to one side. Suppose the ball is trying to escape to, say, that side. Suppose the ball tries to go that way. Then where will more air flow? This side?
That side, yeah.
So what will happen to the pressure here?
Decrease.
And so it will tuck it back in. Make sense? Yeah. So it can't go anywhere. It has to get back into the right place. It cannot go anywhere else. Now, if you come quickly here, I'll show you something more.
Wait, what?
So,
Why should it flip?
like, how does it? Because it's not flipping vertically like that. Because the cop will like come like that, and then the car will flip horizontal.
Oh, probably just because of the push on the side.
Force.
It's just from the force.
Didn't know if it was force or pressure, Kate.
Yeah, the spoilers actually.
There's
The-
literally force going forward. And
The spoilers will take care of it will spoil the airflow, and that way it will not let it lift off. So that is something that again works on Bernoulli's principle. In golf, we talked about tennis, we talked about ping pong. In golf, why is the golf ball pitted? Why are the dimples on the golf ball? It is because it needs to trap air. It needs to trap air. And why air is important? Now, for a short distance, punting and all that, you don't require, the club is going to be flat, right? If the ball is going to be just, the hole is right there and you just like tap it, the club is like this. But if you're going to hit a long shot, which way is the club? What is the angle? The club is angled like this. So when you hit the ball, you're hitting the ball from underneath like this. So when you hit the ball for a long shot, you're making the ball go backspin. And why backspin is important? Why can't you just slam the ball? If you slam the ball like that, the ball is going to go a projectile motion, bounce, 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 bounce. And so you can't make it stop where you want it to stop. So when you hit it from underneath, give it a backspin, what will happen is, when the ball is spinning backward like this, look at the air. More air will flow on the top, reducing the pressure here and increasing the pressure down there. So what will happen? It will get a lift upward. So the ball, instead of going like a projectile motion, it will get scooped up and then it literally drops down. So this will be the trajectory of the ball. It literally drops down, and sometimes it can even spin backwards, move backwards. It all depends on how you hit it. So one thing is there, it loses its forward momentum, and so it might stop there. But if you just throw it like a projectile motion, it'll keep bouncing and going. You can never make it stop somewhere, right? So this is the reason why the clubs are shaped like that, and when you hit it, it is given a backspin at the same time it's given, so it lifts up, goes the distance, and literally falls straight down. Literally falls straight where the hole is. So in golf, yes. So in golf you use Bernoulli's principle. So it's used in all different sorts of places. It's all the pressure difference that matters. It's a pressure difference. So if you look at the river back again, the river is narrower here and then greater there. Where is the pressure high? Where is the pressure high in the fluid? On the left side and right side, the pressure is high. It's lower here. The pressure is lower here because it's faster here. All right, so if there's a tube letting water go like this is exactly what happens. If I connect a pressure gauge here, it will show high pressure. If I connect a pressure gauge here, it will show high pressure. But if I connect a pressure gauge here, it will show lower pressure. If it's a tube. And this is the idea behind airspeed indicators. When a plane is flying, how is the airspeed measured is by a system like this. Yeah.
I always thought that pressure was like always higher in like closed space. Like if you had a bunch of gas in like a tiny container,
yeah,
there
if
would
you,
be
if you
more
compress
pressure.
it, yes.
But then the same gas in like a big container, there'd be less pressure.
That is true. That is true. But we are talking more about the motion. Yeah. If you contain more gas in the same container, it will be higher pressure. But we are talking about the movement of fluid. Movement. Like suppose there's high wind outside. Have you seen the door that leads to your deck and all that? Have you seen that glass door kind of bulge outwards? It wants to explode outwards. Have you felt it? In high winds, that's why they say don't stand next to those doors. Because those doors, outside pressure is low because of the high winds, and inside you're comfortable inside at high pressure. Outside is low. So what happens if the outside is low and inside is high? There's a chance that it breaks up. And if it breaks, it's glass, and so that can be harmful also. Yeah.
So is pressure like the reason why people like get headaches and all when there's storms? Because like the atmospheric pressure kind of changes.
It messes things up, yes. It messes things up really bad. Pressure difference is what causes all that. Now, when you're flying in a plane, you are sitting inside a pressurized cabin. It's a cabin which is pressurized, like a balloon. When you're flying at 40,000 feet, outside pressure is very, very low. So if there's an explosion at that point, there's no survival possible. Because all of a sudden your body is subjected to very high pressure, very low pressure, which will make your body really burst, pop. So survival is difficult. Well, it is possible that the leak of air becomes gradual. Suppose only a tiny hole appears somewhere, some panels kind of break off, and then the little hole is only produced. So definitely what's happening is all the pressurized cabin, the pressure will go down, right? Go out. Because it's highly pressurized. It's not like if a tiny hole is on a balloon, will it pop? No. If a tiny hole is in a balloon, it just leaks the air and loses its pressure and shrinks and shrinks. And the same thing in a plane. If there's a tiny hole somewhere, which is going to get bigger, so what will happen is the pressure in the cabin will start dropping. And that's why they say, in case the pressure drops for some reason, these things will come down and then put it up. So they have this compressed air inside, which is going to supply you the needs for oxygen breathing. But that's only for slower situations, not sudden situations. It's happened in the past. I don't know when, I don't know where. I've seen the pictures of it. It's a CRJ plane, a smaller plane, but the aluminum panels started peeling off. And as soon as they started peeling off, all this dropped down, and then the plane, immediately the pilot starts descending because he doesn't, he can't fly at that high speed. So he reduced the speed and started descending. But as he was descending, this thing was peeling more and more peeling off. By the time he actually landed, He ended up landing, but almost the entire roof is gone. And out of many people, just maybe 1 or 2 casualties, but otherwise everyone was safe. And so everything peeled off, but it happened gradually. So everyone could adjust with that pressure differences. You know what I'm saying? All right, so that's about fluids in motion. So we saw Pascal's principle, we saw Bernoulli's principle. Now we're doing Archimedes' principle. Archimedes' principle. This is a very important one and a very conceptual one at the same time. A lot of problems can be based on this Archimedes principle. So let's discuss about what is Archimedes' principle. Before discussing it, let me go over it in detail. Suppose there's a fluid sitting there. If there's a fluid sitting here, what's the pressure on the top of the fluid? Atmospheric pressure. Very good. The pressure on the top is atmospheric pressure. Now suppose you have an object inside. Suppose you have an object inside the fluid. The pressure is atmospheric pressure on the top. What is the pressure at this level, on the top of this? What is the pressure here? If you're talking about a depth of H1, what's the pressure there? Yeah, in addition to that. So the pressure here is absolute pressure is this plus H1 rho G. Correct? Now what is rho?
Density
Of what?
water.
Of what? So let me call it rho F, which is the density of the fluid. Let's call it rho F. So the pressure here is atmospheric pressure plus H1 rho Fg. Make sense? That's the absolute pressure. What's the pressure here at this height? H2. What's the pressure here? The pressure here is going to be P atmosphere plus H2 rho Fg. Andrew? You understand this? Where's the pressure higher? Where's the pressure higher?
Top.
At the top the pressure is higher, or the bottom the pressure is higher?
They're
Bottom.
equal. They're equal.
Bottom. Look at the height. This is the pressure at the bottom. That's the pressure at the top. H1 is definitely small. So deeper you go, the pressure is higher. So definitely this pressure is bigger. So this pressure P2 is bigger than pressure P1. Pressure P2 is bigger than pressure P1. And that is pressure P2. That is pressure P2. And P1 is that one.
Is that why things float? Because the pressure.
We're getting there. So the pressure is higher here, pressure is lower there. And you know pressure equation is what? Force over?
Area.
So what is force? Pressure times area. So if pressure is P2, there is a force F2 acting here. And there's a force F1 acting here. Which force is bigger? F2 is bigger. F2 is bigger than F1. So the push from the bottom is more than the push from the top. This is only by the fluid. So right down here, what is the net force by fluid? What's the net force by fluid? F2 minus F1. F2 minus F1 is the net force by the fluid. Net force by the fluid is F2 minus F1. And what is F2? F2 is P2 times area, and F1 is P1 times area. Right? So I'm going to put that. P2 times area minus P1 times area.
there ever a point where the pressures can equal and something can just stay floating like
We are
underwater?
getting there, we are getting there. Hold on. We are getting to all those things right now. Just have to. Did you grasp so far?
Yeah.
Good. Now I can take area common out. Is that okay? From that equation, area is common. Now what's P2? I'm going to put it down. What is P2? P2 is P atmosphere plus H2 rho F G. And what's P1? P atmosphere plus minus H1 rho F G. This is P2 minus P1, then times area. I'm just subtracting. I'm subtracting this from this. You can see that very clearly. And what you can see from here? Atmospheric pressure is gone. That means the pressure above the fluid does not matter. Now what is inside? H2 rho F G minus H1 rho F G times area. What can you take out common?
G.
And
Rho F.
so it's H2 minus H1 times rho F G area. Now, don't worry much if you don't understand these things in detail, but try to follow it.
Why is it minus H1?
Because of this.
So wouldn't that just make the negative?
So this negative goes to both of these.
Okay.
Get it? When you open the brackets. Okay, what is H2 minus H1? Isn't that the height of the block? H2 minus H1 is the height of the block. Okay? So it's the height of the block times rho F times G times area. That's the height of the block. H2 minus H1 is the height of the block. Now what is the product of height of the block and area? What is that supposed to be? What is the area? Huh?
Volume.
Volume. That's right. That's a volume of the object. Volume of the object. This is the volume of the object. Density of the fluid times gravity. Volume of the object. Isn't that the same as the volume of the fluid displaced? Isn't the volume of the object the same as the volume of the fluid pushed out? Yeah? Like, I've got a certain volume. I have a certain volume. Before I went to that place, what is there is air. If I am taking that position, I'm pushing the air and settling there, right? How much air did I push out?
Whatever is equivalent to you.
Exactly. So this volume of the object is the same as the volume of the fluid. Volume of object is equal to volume of fluid displaced. Because it's fully inside. It's fully inside the water. Or inside the liquid. So we have Vf times rho F times G because these are equal. Now what is the product of Vf and rho F? What's the product of Vf and rho F? That's the first thing we did in this chapter. Density is mass over volume. You're right. Density is mass over volume. That means what? Density of fluid is mass of fluid times divided by volume of fluid. So what is the product of volume and density? These are all equations that you're definitely going to use. Mass of fluid displaced is this. So this is mass of fluid displaced times gravity. What is mass times gravity?
It's weight.
Weight. So this is the weight of fluid displace. Now, if you did not understand all these things or lost track of all these things, it's okay. But you need to know this. The net force offered by the fluid is called buoyant force. The net force offered by the fluid is called the buoyant force. Okay? So the buoyant force is the net force offered by the fluid, which is equal to what? The weight of the, that is Archimedes' principle. That is Archimedes' principle. Can you write down the whole principle down in words, everyone? Or should I write on the board? Okay.
Force equals the weight of fluid displaced.
Yeah, but I'll write it down. Okay, I'm taking this out. Archimedes' principle is this. When an object is partially or fully submerged in a fluid, it experiences an upward force called buoyant force by the fluid which is equal to the weight of the fluid displaced by the object. That is your Archimedes principle. When an object is partially or fully submerged in a fluid, it experiences an upward force called the buoyant force by the fluid, which is equal to the weight of the fluid displaced. That's your Archimedes principle. It's a very important principle, and you saw some of the equations right there. Now, so this object is now going to suffer two forces when it is inside. One force is the weight. I'll call it gravitational force. The weight is a gravitational force, right? Mm-hmm. And what's weight? Weight is the mass of object times gravity. Mm-hmm. Can you write the mass of object as volume of object times density of object times gravity? Mm-hmm. So the weight can also be written this way. And the buoyant force is how much force it experiences upward. That's a buoyant force, that one, which is mass of the fluid displaced times gravity, which is volume of fluid displaced times density of fluid displaced times gravity. So you can see this. Yeah, these are the most important equations which I'm writing here. These are the most important ones. Okay, as I said, the derivation is not that. Of course, derivation is useful to understand the Archimedes principle, but you don't have to worry about the derivation much. You should be more worried about these equations. So, all these equations that I've shown here. So what is buoyant force? When an object is partially or fully submerged in a fluid, then it experiences a buoyant force upward, right? Mm-hmm. Which is equal to the weight of the
fluid displaced.
fluid displaced.
Well, it's in water right now.
Right.
Magic trick or clock.
Now, let's go for some magic now. But the magic is only on the board. No, not that. No. That's a bowling ball. That's a bowling ball. And that is a balloon. This is a bowling ball and this is a balloon. They look exactly the same. The diameter is exactly the same. You get it?
Yeah.
That's a bowling ball, that's a balloon. They look exactly the same. They're identical in all manners. The diameter of this and the diameter of this is same. Everything is same. Question is this. Which one experiences more buoyant force?
Same.
The balloon. No. Bowling.
Is the weight the same?
Equal.
No, they're not.
These are both in air. Like this is a bowling ball. That's a balloon.
No, it's the balloon. The balloon goes up.
No, like
Equal.
characteristics, not like a balloon. It goes up and it's pushed by the fluid.
Balloon.
Balloon.
What was your answer, Ben?
They're the same.
They are the same.
I said that 3 times.
I said it before anyone said it.
I said that, you said that. No.
All right. Now, why is the buoyant force the same? That's my question now. What is the buoyant?
First.
It's the volume of the fluid displaced.
Is the same. That means the mass of the air displaced by both of them is the same. So it doesn't matter what is inside. The buoyant force does not matter what is inside. The buoyant force only looks at what's the weight of the fluid displaced, not its own weight. Not its own weight. They both have the same buoyant force. Watch. The buoyant force offered on here is FB. The buoyant force offered on this is also FB. They're both the same. Look at the arrows. But then why is this falling so quickly and the other one doesn't fall that quickly? It's because the weight Fg is much bigger on the bowling ball. And the weight on this balloon is a little bigger than the buoyant force. Can you see that? Because it's air. Now what if I have a similar balloon with helium inside?
Ooh. It's gonna be lighter.
What about the buoyant force?
Same.
Same. Doesn't matter. Same buoyant force. And what about the weight of the helium balloon? Is smaller. That's why the helium balloon goes up. But the normal balloon sinks, but not too fast. But this bowling ball kind of falls really hard, right? Do you understand the idea? Clear? So understand. Don't make mistakes on these questions. They may be a little tricky like that,
So
but
helium's lighter, and that's what makes it.
lighter.
Yeah.
Why the weight of the entire thing is light is because helium is much lighter than air. All right. Another one now. Hey, not finished yet. Not finished yet. If I place a soccer ball on water, will the soccer ball settle like this? Is that the way a soccer ball is going to settle on water?
No.
No. Why? Because if it settles like this, there's only one weight which is acting downward. That should not be in equilibrium. Will the soccer ball settle like this?
Yes.
No.
No. Because this means like so much water is displaced, the buoyant force will be really big compared to the weight. And that's a pretty dangerous thing to do, right? When you try to push a ball into the pool with your hands, it's very dangerous. Because what happens is the buoyant force is really strong and the ball becomes slippery once it's inside. And it will release itself from your hands and come straight at you and hit your nose. So that's dangerous. So what really happens here? What really happens is a little bit of the ball is inside the water and the whole thing is balanced. This is flotation. So what's happening here? Which one is more? The buoyant force is bigger or the weight is bigger?
Weight is bigger.
They are the same.
I said that.
Okay, you said
You
it.
didn't say it.
Yeah, I said it the first time.
I said it.
You said it's bigger. I said
I
equal.
was the one who said it in the first place when we talked about the first.
Just this question you just asked. I said equal.
Yes, this.
That's what we call as flotation when these two are equal to each other. Okay?